So at the end of today's lecture, you will be able to analyze problems involving different forms of work. For an example, spring work, boundary work in various thermodynamics processes, right? So we learned how a substance expand, how a substance compress and whatnot with a simple piston cylinder mechanism. And we are going to learn what's going to happen in systems when springs are there and what is the work component involved and stuff. And also, by the end of today's lecture, you will be able to apply the first law for closed systems. Now you see the importance of the definitions we learned in the beginning of this course, like closed systems. What is a closed system? A system in which the mass cannot cross the boundary, but the energy can. Okay. So if you are interested in further reading, you can go for chapter 4.1, go from chapter 4.1 from to 4.8 in the recommended text. Okay, so I'm pretty sure that all of you already watched the video that I've uploaded and you are pretty familiar about the process that we have here. Just to recap your memory or refresh your memory, like we'll go through one by one. A constant volume process in which the total volume or specific volume is constant, we can call it an isochoric process, right? So in a question or in an exam setup, like if you see a rigid container, a sealed tank or something like that, then it kind of interpret, or it kind of gives you the sense that okay, the volume is not going to change, right? So this is a big help if it is the case. So as you see that kind of a term, then you know, okay, my PV diagrams are going to be on an isochoric line, right? So basically, if it is in a PV diagram, PV, then an isochoric line would look like this, a vertical line, right? Then then we have isobaric lines where the pressure is constant. So in the PV diagram, isobaric line would look like this, right? And isothermal lines, constant temperature, like in isothermal processes, the temperature does not change. So it would have a shape like this, but like a curved shape. This is not the perfect way to draw it. Let me get a different color, like this shape, right? So this would be an isothermal process. So by looking at the curve, we cannot say whether it's an isothermal process. By looking at the PV diagram, we can just simply say, okay, this is an isochoric process, this is an isobaric process. If we mark an isothermal process in a TV diagram, then it's pretty simple to say, because isothermal processes on TV diagrams would look like this, right? Because temperature is the y-axis. And we have isentropic processes where the entropy is constant, but at this point we have not learned what is entropy, and therefore we pause it for now. Keep that concept in the refrigerator and we'll take it out when the time is right. Okay. And then we have adiabatic processes, like where there's no heat transfer, right? When you say an insulated container or insulated system, right? Insulated tank, something like that, there's a high chance it could be an adiabatic process. If it is a closed container and well insulated, then heat cannot cross the boundary, then that means it's an adiabatic process. Okay, so in question it could come in two ways. One way to mention this is a well insulated tank or something, or well insulated system, or the other way is this is an adiabatic process. So either ways you should be able to understand these terms, right? And at the last we have the most important process of the day, and that is polytropic process. In the previous lecture, as I explained, any process, if we can write it as PV to the power n equals constant, if any process that follows this format can be called a polytropic process, right? So most of the processes that we discussed above can be presented as a polytropic process, but they have more important characteristics than being polytropic, right? Because like if it is isothermal or isobaric or isochoric, we can use that feature to solve the questions rather than looking it to be a polytropic process. But there are some processes, there's no any other special characteristic like being pressure constant, temperature constant, or whatnot. So in such a situation, this polytropic equation, if the process is polytropic, then that is very important, or that makes our life easy during tackling the problem, right? Okay, so as I mentioned, we can use the polytropic process to present different processes, right? Depending on the polytropic index n, the process type, the shape of the curve, everything changes, right? And this polytropic index is a constant for a given process, so the number can vary depending on the conditions. Let's see one by one. If a polytropic process is presented by, if the polytropic index is equal to gamma, right, n equals gamma, then that process is called an adiabatic process. We know the other characteristics of an adiabatic process. There will be no heat transfer crossing the system boundary, across the system boundary, right? In addition to that, we know that the polytropic index of this process is going to be equal to gamma. Gamma is the specific heat ratio. So we will discuss what is gamma exactly, like in the coming lectures. But once you know that it is gamma, in a question, if we say that, okay, there's an adiabatic process of which the gamma equals this much, then we know that, right? So the second one, when n equals infinity, the polytropic index becomes infinity or is very large, then we can basically say volume is constant, right? So in such a situation, the volume is becoming a constant. So some of you may be wondering how this thing happens. So let's try to get a sense out here. So let's assume that PVN equals constant. So then if we take the nth root of both sides, then P to the power 1 over n, V equals C to the power 1 over n, right? So by looking at this, what can we say about the impact of pressure on this relationship? If n is a very large number, if n is infinite, if when pressure changes, does this overall term changes too much? Can anybody answer? When the pressure changes and n is reaching infinity, right? When n is reaching infinity, what can you say about 1 over n? What can you say about 1 over n? Pressure goes to 1. Not exactly. Yeah, pressure goes to 1. Alexandra, you are correct. Okay, my bad. So when 1 over n gets closer to 0, then p to the power 0 becomes closer to 1, right? Then in that case, no matter what the pressure value is, our p to the power 1 over n is not going to change significantly even if we change the pressure. So in that case, we can assume this becomes very close to 1 and it's going to stay there. And in that situation, on the right side, we have a constant. Therefore, V is going to be constant as well. Are we all clear on how that happened? I'm not going to check you on the derivations, but I'm just trying to explain so that you can enjoy, because rather than just memorizing, okay, this happened, I'm trying to give you some context here. That's what it's all about, right? So if you take the nth root of this equation in both sides, then you can get that expression. Okay. So if you don't understand the derivation, it's fine. Just remember, when n is very large, it's a constant volume process or isochoric process. Okay. When n is equal to 0, this is very straightforward at that point. So p to the power 0, v sorry, p, not p to the power 0, pv to the power 0 is equal to a constant. So this parameter becomes 1, therefore p becomes a constant. So if n equals 0, we can say that is an isobaric process. Okay. And when n equals 1, we can say that pv equals constant. So in an ideal gas situation, if pv equals constant, that means we can assume this to be an isothermal process, even if not an ideal gas process. Let's say for a real gas, we can say that pv equals zRT, right, without any issue, like specific volume here. If you did not have the specific volume, instead if you had the volume, then it's going to be pv equals zMRT. Okay. So this ZR and R are constant for a given setup. Then if PV equals constant, temperature is going to be a constant. So that means it's an isothermal process, right? So you cannot make your own formula sheet, but you can use the formula sheet under the important documents. So you can download it from the canvas. Okay. Alexander, did I answer your question? Perfect. So up to this point, do we have any questions or any issues that we have as of now? Any problems? Perfect. So let's move on. Now here you see the PV diagram of an ideal Otto cycle. Why we say it's an ideal Otto cycle? So in reality, you won't see these sharp edges and whatnot. So like the things get a little deviated from the ideal. So the curves might look a little curved, like the edges and all these things, right? These points might not look this sharp, but in an ideal situation, like we can explain the setup like this, right? So what is an Otto cycle? So the Otto cycle is the cycle that all your gasoline engines work. Your first 4-stroke gasoline engines work under this cycle, right? So it's very important. Your daily ride is operated on this one. Let's see how we can try to draw a PV diagram for a known process. Okay, so if we start with the inlet stroke shown in the first diagram here, so if we start with this one, what happens the first in inlet stroke? What happens is we open the valves so that we can inject the fuel air mixture into the chamber, right? So in this case, as the valve is open, when the piston moves downwards, there will be no pressure difference. Are we all agreeing? Any doubts about that? You can put it in the chat if you have any doubts. So the valve is open, so now pressure is not going to build up, so we come this way, right? So the volume is increasing because the piston is moving down, still the valve is open, so pressure, no pressure build up, but the volume is increasing 0 to 1. And from 1 to 2, now we have closed the valve, inlet valve and exhaust valve. We have closed everything. Now it's like a tank, right? An enclosed space. So now we move the piston upwards. Then what can we say about the volume? Volume is going to reduce, right? But in a closed space, if we reduce the volume, we definitely know that the pressure is going to reduce or increase, right? There's a pressure buildup. So therefore, we definitely know that the process from 1 to 2 is going to go in this direction as marked. But what is it? Is it a straight line or is it a curved line or whatnot? So we have to determine that. So there we make an assumption. The process happens so fast. Therefore, when the process happens so fast, we assume that there's no enough time to emit heat to the outside, right? There's no or minimal, right, heat loss to the surroundings. So then if there's no heat loss to the surrounding or heat gain from the surrounding, then such a process can be called adiabatic, right? For adiabatic processes, we learned PV gamma is equal to a constant, where gamma is the specific heat constant, right? So in the question, you might see there's an adiabatic process going on and whatnot. Within brackets, maybe you see the specific heat constant is this much. Or if it is not given, you can go to property tables and find specific heat constant as well yourselves, right? So anyways, back to the topic. So now, following an adiabatic process, our compression stroke goes this way, right? And now we are at the top of the cylinder, right? There, what happens next? When the injection plug comes into the picture. So spark plug, sorry. This is not a diesel engine, so there's spark plug. So spark plug introduce a spark to this fuel air mixture. Can we guess what's going to happen? Obviously, yes, because this is a combustible mixture. So when we introduce a spark, then it's definitely going to detonate the mixture, right? So with that, at the first instance, when the burn happens, it happens so quick, the fuel air mixture burns on the spot. Therefore, we can assume for a bit of time, the is not going to change, but the burning is going to happen, right? So there we mark this as a constant volume heat addition. With the burning, the temperature increases. When the temperature increases, the gas tries to expand, therefore a pressure build up, as the pressure has not changed yet, right? Any questions up to state 3? Okay, so now when the gas has the energy, then it definitely pushes the piston down, right? So when a gas is pushing the piston down, that means it's expanding and doing work on the piston. From the previous lecture, the video I uploaded, you remember when a gas is expanding, then it is doing the work on the piston. So the work done by a gas can be told as positive work. So that is an agreement that we have. Anyways, we'll discuss that matter later. So now we are at here. So now the gas is trying to expand in expansion power stroke, right? There again, we assume that this process happens so quick, so the heat loss to the surrounding is minimal, right? So now, therefore, similar to process 1 to 2, we assume that process 3 to 4 is going to be an adiabatic process. Okay, and when the power stroke returns, now like after piston goes down, then the crank moves it up again, right? During that, we open up the exhaust valve. When the exhaust valve opens, like then 4 to 1, the gas is going to go out, right? As the gas go out, we had an excess pressure compared to atmospheric pressure, right? So then there's two pressure values at the two ends of the valve. So then we are going to reduce the pressure inside the chamber, right? Therefore, we drop the pressure for a bit of time. Initially, we assume this happens at a constant volume. First, we drop the pressure until atmospheric pressure in the constant volume, and then we sweep up the piston. And as we sweep up the piston, then the combusted or burned air mix, fuel air mixture is going to go out. And once it reaches atmospheric pressure, there will be no pressure loss anymore. It will be only volume reduction from 1 to 0, right? So you will not be tested on this cycle in your exams, but what I have wanted to let you know is that these simple thermodynamic concepts that we learn, adiabatic processes, isobaric processes, isochoric processes, like initially even I felt these are boring concepts when I learned these at the first instance, but these can be used to interpret the processes that are close to us. This is how your engine works, right? So at least this is how your energy transfer works inside your engine. So you can see why learning these concepts are important. Okay, so now with that being said, wait, so is this the same slide? Interesting. So I made a little change here. Anyways, we'll discuss as we go, right? So when we derive the work in the last lecture, we derived the work for isothermal processes, right? When the n equals 1 in a polytropic process, when n equals 1, then this becomes PV equals constant, right? So we agreed when PV equals to a constant, that can be written as an isothermal process. That can be recognized as an isothermal process, right? So the work done during an isothermal process is going to be given by this expression that is circled here, right? So why do we have two expressions here? P1 V1 equals ln V2 over V1 and P2 V2 into ln V2 over V1. Are these, I mean, if we calculate these two expressions, let's say expression A, expression B. If we calculate expression A and B for an isothermal process, are these going to be similar or different? It's going to be the same, right? Because we said that PV equals a constant. Basically, we can say that P1 V1. This is the conditions at state 1, right? Equals P2 V2, right? So that means that's going to be equal to a constant, right? So you cannot see the screen. Okay, that's the first. Let's say I'll try to stop the screen and turn it back. Can you see now? Awesome. Well, that's the first. Anyways, so you will understand that we can write this expression, right? So no issues there. And for an ideal gas, we know that we can write the expressions, the relationships in MRT, right? So for an ideal gas, so PV equals MRT. So basically what happened here is substituting for PV in temperature terms. You can put T1 or T2, like it doesn't really matter. T1 or T2 because it's going to be a constant MRT. P1 V1 equals P1 V what no T1 V1 equals like this one, this expression. So this is P2 V2. P2 V2. Okay, so you can see this relationship, the relationship circled in yellow, can only be used for ideal gas, right? Gases. So this is the thing that I edited last night, but for some reason it's not here, but you understand the idea. Any questions so far? Okay, so now if we divide this entire equation by mass term, like the mass of the system that we are interested in, then it becomes specific work, right? So work becomes specific work, and then we don't have to divide each and every term by mass. Like when we divide the right hand side, when we divide, let's say what we do is we divide everything using mass, right? When this happens, work becomes specific volume, and we divide volume term in this expression, and then it converts into specific volume here in the bottom expression, and here also volume becomes specific volume, and here the mass is gone now, right? So are we clear? Like we can write this expression in total volume or specific volume terms, but like if we use specific volumes in these expressions, then what we get is the specific work, right? Inside the bracket, does it matter whether it's specific volume or total volume? Inside the bracket, there's no bracket, but I mean inside the log term, the ratio. When it is a ratio, does it really matter? It doesn't really matter, right? So the mass cancels out, so it doesn't really matter. For a closed system, the mass cannot cross the boundary, so therefore it's very easy and convenient. So in a process where n is not equal to 1, so basically when n is not equal to 1, it's not going to be an isothermal process, right? So we know that as well. So however, if n is not equal to 1, we can use these two expressions to present the total work or specific work, right? So we did the same thing. This is the total work expression, and if we divide everything by the mass, then we can get the specific work expression, right? Total work and specific work. And if you check your formula sheet in the canvas, you will find all these expressions, right? So the important fact is when and where we can use these relationships. You have to know these, right? So if the substance of interest is not an ideal gas, you cannot use this portion of this expression, right? This portion of this expression is not cannot be used, but the other parts can be used, right? So are we all clear? Any issues? Perfect. Let's get going now. Perfect. Thank you all for the feedback, and thank you very much for being involved in the class. It's very important. So it gives me some feedback so that I can direct the lecture, right? So now, at the beginning of this lecture, we agreed that we are going to learn the work required to compress or expand a spring to a certain distance, right? So if we see spring work, then we can use this equation to write that. So the work expression, like in our classes, in our early classes, we learned that if we have a weight, let's say on a surface, a smooth surface or rough surface, doesn't matter. So if we have a force, we apply a force like this, and then this substance or this cube travels a delta x distance, then we wrote the work done by us on this cube as f delta x, right? I hope all of us are familiar with that one. So for a very small distance, we can call this delta x as dx, right? So dx is a smaller version. You can assume that to be that. So if this is point 1, this is point 2, and if this force is a variable, let's say if this force is a variable, then we can integrate this along this line using this expression from x equals 1 to x equals x2. We integrate the force by the distance, right? For a spring, we can present the work as, we can present the force as k into x, right? So from the initial position, if our from the equilibrium position, if our spring is compressed or expanded an x distance, so the force that can be, that is applied on the spring should be equal to k x. K is the spring constant, right? So now when we integrate this one, we come up to this expression, right? So if you do not understand the integral or how did we did the integration, don't worry about that as at this point, because our focus is not to learn integration here, but to learn how much work is needed to compress or expand a spring, right? So this applies both ways. So even like if you have held a spring on your hand, like a smaller one or a big one, you know that no matter what, whether you're trying to compress it or you're trying to expand it, so either ways you have to do work, because it's not going to let you do that, right? So it's resisting your movement, so you have to do work. Okay, so in this final expression, x2 is the final displacement, like x1 is the initial displacement from the equilibrium position, right? So during this x1 and x2, this much work is done. Any questions? Perfect. And now let's move on to the next portions. The interesting stuff, the practice example, right? So try to draw this one real quick. Draw the PV diagram for the gas inside when the setup is heated, right? So, and mark the work done during the process using the area. Okay, first try to draw the PV diagram for this one when the setup is heated. take 2-3 minutes, maybe 2 minutes to think about this one. Yeah, there's no T on the graph. I am aware about that, Penna. Like, draw with whatever the parameters you have on the graph. I want to see what happens to pressure and specific volume. Okay, Robert, you have one gas, slight increase in volume and a large increase in pressure. Not exactly. No, that's not the thing that's happening. That's not accurate. Okay, so let's try to understand this process together, right? So it's an isochoric process, excellent. So the volume is not going to change, right? So this tank here does not have any moving boundaries, right? So in this case, therefore volume is not going to change. So when the volume is not going to change, we know that no matter what, the process is going to be on a vertical line like this, right? And then it says we heat it up, we heat the setup. So when we heat the setup, then what does that mean? We increase the temperature of the process, right? When the volume is constrained and we increase the temperature, the substance tries to expand. When the substance tries to expand in a constrained space, then that builds pressure, right? So that means we are going upwards in this direction. So this is a vertical line. It looks like a worm or something, but it is supposed to be a vertical line, just a vertical line going up. Okay, so clear about this one? Think of a time when you eat too much, then sometimes your clothes may be fit so tight, your stomach is so big now, and like the shirts or the dresses that we are wearing, it's going to be tight, right? When we try to expand, it builds up pressure in a constrained space. When we try to expand, it builds up pressure, right? Nice. Now try this one. Now don't assume that there's a phase change. Assume that it is in the gaseous phase throughout. Adiabatic, we don't know. Isochoric, you can see if you try to interpret the problem. So that is the problem. Whether it's isochoric, isobaric, how can we interpret pressures and volumes? Isochoric, but P decreases. Okay, that is one way of seeing it, but it's not accurate. So let's try to interpret this one together. Okay, so now if the system stays in balance, then what can we say about the pressure that we have here? So the substance should have enough pressure to hold the piston, right? If it have more pressure, then it would not be stationary like this to start with. It will be further expanding, right? So if the pressure is just enough to maintain the equilibrium of the weight, so then it will stay like this. Do we all agree? Do we all agree? Okay. So if we want to find the pressure on this top surface, then what would we do? We'll get, this is the weight of the piston, and this is the force applied by the atmospheric pressure, right? A is the area of the piston. Do we all agree there? So if we want to balance these two forces, then we can apply a counter force by the gas. The pressure of the gas does this, right? P gas, let's say. P gas. So in this case, by the force balance, we know that F minus mg minus P naught A equals 0. Do we all agree here? And the pressure applied by the gas is given by F. So we can write this as PGA minus mg. PGA equals mg plus P naught A. Divide the entire equation by area. So P gas equals mg plus P naught. Mg divided by A plus P naught. Right? So this is the pressure at the starting point. So when we cool, what happens? When we try to cool, then the temperature reduces, right? So that is obvious. When the temperature reduces, that is what we call as cooling, right? So if you put up a can of pop in the refrigerator and then we say that, okay, it's cool, and when we take it out, you don't see any temperature difference, then you'll be pissed, right? So it is definitely a temperature drop, right? So when we are cooling, the temperature drops. So when the temperature drops, there are a few things that can happen. Either pressure can vary or the volume can vary, right? So in this case, when the temperature drops, the gas squeezes a little, right? Gas, the volume reduces a little, but still the weight of the piston is acting upon the gas, so the pressure is not going to reduce. This is a closed container. What is the definition of a closed container? No mass cannot enter the system or leave the system. Is there a mass entering or leaving the system? There's a piston, right? This is a piston. So the one we see up there. So now the piston drops and I keep compressing the liquid, right? So until it reaches these stops, what can you say about the pressure? Is it going to change or is it going to stay constant? What can you say about that? Anybody? Until this piston reaches these stops, is the pressure dropping or is the pressure is going to be constant? Pressure is constant, right? What can you say about the volume? Volume changes, right? So definitely this process is going to be in a horizontal line now up until the pistons, right? So we'll call this state 1 and we'll call the state when the piston is just touching the stops 2, right? So now we what can we say about the volume? Is it reducing or increasing? Obviously, as we can physically see, the volume is reducing, right? So we can easily say that process 1 to 2 is happening this way. 1 to 2 is happening this way. Do we all agree? Okay, perfect. Now, then from 2, right? Then after the piston hits the stop, what can you say? What happens to the volume when we cool? When we cool the process, then what can we say about the volume? It remains constant. That's very true, because the piston cannot move any lower than the stops, right? So with that, we get an understanding. Okay, now our process going to be on a vertical line, right? And now we have the question whether the pressure drops or pressure builds up as we cool. Pressure drops. That's very true, right? Because we reduce the temperature and the volume is constant. So the gas contracts, like, but there's more than enough space for the gas, like more than the space that is required for the gas. Now, so the pressure should drop down now, right? So then this is going to be our final state. Let's say it's 3. Let's say it's 3. Okay, are we clear? Any doubts? Perfect. Right. Now it's getting more and more interesting. Now we have a spring-loaded spring, right? So try to write or try to draw the PV diagram when we heat this up. Okay, so in the previous questions, we forgot to do one important thing. What is the area covering the, like in the first one, we did not have any work done. There was no area covered, right? Because like the process was like this. And in the second one, what is the area covering the work? So area given by PdV, right? So basically, this is going to be the area that indicates work. Do we all agree? Or any doubts? Perfect. So now here, from 1 to 2, is there work or no? No work. There's work. Okay. So is it done on the system or done by the system? Perfect. It is done on the system. How do we determine that? When a volume is reducing, we know that the work is done on the system. So basically, just physically understand this one. So when we have a piston, if we have a gas, if the piston has to move in the direction of the gas so that the volume reduces, we have to press it, right? So nobody else would be doing that. And if the system is expanding due to thermal properties, then that expansion means the system is doing work on the surroundings, right? Okay, from 1 to 2, there's work, and that work is done on the system. And from 2 to 3, is there any work, or is it done on the system or done on the surroundings? From 2 to 3, there's no work. Excellent. So because there's no volume change, so this brings us to an important notion. When there's no boundary, when there's no volume change, then there's no boundary work involved in the process, right? Okay, are we clear about that one? Anybody having issues? Okay, Perfect. So now let's try this process. Try to draw the PV diagram for this process. V increase until piston touch the top. V increase definitely yes. P keep the same and then increase when piston touch top. That part that is not accurate. Pressure and volume increases until it hits to higher spring resistance, and then only pressure increases. Pressure and volume increase, yes, both increase at the beginning, and then when until the spring cannot further contract or it hit the stop. So either of those. So then the volume change stops, but the pressure keep on building. That's true. So now think about the pressure variation and pressure volume variation during the first phase, right? So what happens here? Let's try to understand together. So when we try to heat this up, then the gas tries to expand, right? When the gas tries to expand, what does the spring do? Spring add more force, right? So as the spring force increases, you know that when we compress a spring, the force applied by the spring or applied on the spring has to increase in order for us to push it further, right? Because F is equal to Kx. K is a constant, this is spring constant, X is the displacement, right? So further and further we push this one, so more and more force is needed. So that means when more and more force is needed, so if this volume is expanding, that means more and more pressure is building inside the chamber, right? So as Kylie mentioned, when the system expands to its full potential until it hits the stops or until the spring cannot be further compressed. So let's say piston reaches this point. Now the volume stops changing because it cannot go any further, right? The piston cannot go any further. Now the pressure starts building. Now the pressure starts building. That part is pretty simple. That is going to be an isochoric process. Let's say this is 2 and the higher pressure is 3. From 2 to 3, this part is pretty straightforward. The real question is, what happens from 1 to 2? Sorry, this pen is giving me a hard time today. Okay, let's say the starting point, or not this one. So let's say the starting state of the piston this state, the initial state as 1, right? So we all agreed the pressure and volume is going to increase as we heat the system from state 1 to 2. So we know that state 1 is going to be here. State 1 is going to be, sorry, here, state 1. Okay. Now, from 1 to 2, there are many paths that we can take. A straight line, a curved line, and like this. And we need to know what's really happening, right? So how do we know the relationship between P and V? So to start with, we can use a simple force balance equation here and try to solve this one, right? So if we think of the force balance, let's say atmospheric pressure P naught into area, that is one force acting on the piston, right? And then in addition to that, the spring applies a force which is Kx, right? And in addition to that, we have the mass of the piston or the weight of the piston acting downwards. And then all these forces are balanced by the gas of the pressure of the gas into the area of the piston. So do we all agree? Do we all agree about these forces? Are we all clear? Perfect. So if we try for now, like let's say for now, let's move erase this one. This is pretty easy to draw again. So to get more space. Okay. So if we consider the force balance upward, we can write Pg into area minus Kx minus P naught A minus mg equals 0, right? So in this case, we know that this expression exists. So we need to find an expression for P gas with respect to specific volume or the displacement. For now, we'll go with getting an expression for Pg using this one. What we have Pg, and if we divide the entire equation by area, we have Kx divided by A minus P naught minus mg equals 0, right? So you know that atmospheric pressure and piston cylinder are mass of the piston cylinder or weight of the piston cylinder are not going to vary during the process, right? Therefore, we can call that's a constant. This is a constant, right? Therefore, we can say that Pg constant C. Pg equals K over A, which is again a constant, into X plus a constant. Do we all agree? Do we all agree? Perfect. So we can write an expression for X using volume, right? So if we want to write, let's assume the initial state of the piston is equilibrium state is X equals 0 here. And the initial state of the process is X equals X1, right? So then the volume of the cylinder, the change of volume is going to be V1 plus delta V, right? At a given general location, if we see our X is equal to, given at a given location, our displacement is X, and then we can write V equals V1 plus delta V, and V equals V1 plus area into X minus, there's not enough space, give me 1 second to write that again. This equals V1 plus area into X minus X1. Do we all agree? Do we all agree with this one? Perfect. So now you can see that both pressure and volume varies linearly with each other, right? So what does that mean? When both pressure and volume varies with linearly with each other, we can assume that pressure and volume varies linearly with each other. Pressure varies linearly with the x, volume varies linearly with the x, and if you substitute for x in this equation 1, using the expression in equation 2 for x, right? At home, substitute for x, right? So then if you substitute for x in expression 1 or equation 1 from the volume expression, then you can get the relationship between the pressure and volume. Then you'll see it's a linear relationship, right? And K and A are positive constants. Therefore, when the pressure increases, both volume and pressure increase at the same time simultaneously. So yeah, and some of you may be wondering, okay, my God, like this looks complicated, and do we need to do all these calculations during the exam or during whatever, right? If you cannot interpret a system by looking at it, then you better write the equations that you know and try to interpret it that way. But if you know, for an example, if you can see, okay, the pressure and volume changes linearly with each other, then you don't have to do the entire derivation. I will not give marks for derivation, but you have to know what is happening during the process. Are we clear? So now let's get back to drawing our process line. So we draw this process 2 to 3. It was very easy and straightforward and no complicated equations whatsoever. So 2 to 3 we draw with ease a vertical line, and 1 to 2 we understood that it's a linear variation, so we can connect 1 and 2 using a straight line. Anybody having issues on how we arrived here? Yeah, when do you go ahead?
Excuse me, I have a problem about the linear relationship. Yeah, based on the mathematical expression, it's linear relationship. But when I imagine that process, because of the spring, you when the what's word I'm looking for? When the volume increase a little bit, no. I mean, when the volume touched the spring resonance, even
Okay,
the
you
increase a
when
little
it
bit.
comes when
Yeah,
it touches the top, yeah.
no, not touch the top, very close to the top. Even the volume increase a little bit, but we need to use more force, right? That means the pressure increase very fast. Should we use the curve?
No, it's not a curve. Like as we develop the mathematical expression, it's not going to be like this. This is wrong. So the relationship between spring and displacement, we like based on the physical expressions, we develop the relationship. Therefore, it's not going to be a curve. Really. Okay.
Okay.
So it's going to be a linear curve as we draw here.
Okay. Just to use the mathematical expression, right?
Yeah, like the mathematic expressions doesn't mean that it's not happening in the real world. People develop the spring force and displacement relationship by looking at empirical results, right? So it is applicable to practical world. It's not like we are oversimplifying things. It's not like that. In this particular instance, it can happen. It
Okay,
is the way
okay.
it happens.
Okay, I see. Yeah, thank you.
Okay, perfect. So it doesn't matter if the rate of volume increase slows. No. So the rate, like if we had a time, then it's a different story. So the confusion you see here is if you have drawn like the substances with respect to a time axis instead of volume. If we had time, then it would have mattered, but what the variable that we have is the volume, right? So the temperature does not matter, so the rate does not matter. Okay, so now in order for us to draw the work, what can we say about the work done during process 2 to 3? Process 2 to 3. What can we say about the work done during process 2 to 3? It's 0 because it's an isochoric process, no work, right? So the work done during process 1 to 2 can be indicated by this area. So if we want to find this work at a given example, if we wanted to calculate this one, so this would be V2, this one would be V1, and this one would be P1, and this one would be P2. How do we do that? So how do we do that? We know how to find the area of a trapezoid, ne? So like we have area of the trapezoid, right? So W1 to 2, the work done during the process from 1 to 2 is going to be equal to the area of the trapezoid. So how do we calculate that? We get the average of these two heights, these two edges, and then we get P1 plus P2 divided by 2, and we multiply it by this length, which is going to be V2 minus V1. Are we clear about that? So some of you might think this is too simple, like we know how to calculate the area of a trapezoid. I know that, but these simple things sometimes, like in the exam pressure or something, students tend to mistake, right? So don't do that. So think of this as a trapezoid, and you know how to find the area of a trapezoid, and then calculate the work done during the process using that. Okay. Now the next process. Try this one. Take about 2 minutes. Now you have a lot of experience, so you can try to complete this question. Perfect. So isobaric and isochoric, and when this says we increase until the piston touches the top, and P keeps same, and then increase where the piston touches the top. Perfect. Like both of you are right. That is very good, right? So what we have here is like similar to the previous example. The piston, the pressure inside the gas is just enough to hold the piston, right? When we heat it up, then the gas tries to expand, but there's no resistance. Therefore, the pressure will not be increasing, but the volume will be increasing until it hits the stops. So if we consider this to be state 1 and this to be state 2, until the piston hits the stops, pressure is going to be constant, right? Therefore, it's going to be a horizontal line from 1 to 2. And there onwards, we still keep heating, but the volume cannot change because it's constrained by the stops now. And therefore, when the gas tries to expand, the pressure increases. There's a pressure buildup, right? From 2 to 3, let's say, the pressure increased further. This is a vertical line, okay? This is not a curved line or something. This is just a vertical line from 2 to 3 is a vertical line. Okay. So what can you say about the work done from process 2 to 3? Work done during process 2 to 3? No work, right? Process done during 1 to 2 can be given by this area, can be calculated by this area, right? So what can you say about the work? Is it done on the system? Is it done by the system? It is done by the system, because when we expand, then it's done by the system, right? Okay. So any questions? Are we all clear? If we are all clear, so we can go to the next example, and we can take a quick a break of 5 minutes, and you can attend the question in the next few minutes, and let's all meet at 9:30. Or in the meantime, is anybody wondering why don't we draw the dome in these PV diagrams that we discussed today? Why didn't we draw the dome here? Yes, exactly. Very good. So it's not two-phase mixture that we are talking about. So all the things that we discussed up to this point were gases, right? Therefore, that's why we did not draw the dome, right? Okay. Okay, now, let's try to interpret this problem. Okay, N2 gas goes through a polytropic process with N equals 1.3 in a piston cylinder setup. Okay, so you know what a piston cylinder setup, so I'm not going to draw it. So with the polytropic process, what this says is N equals 1.3 means PV to the power 1.3 equals constant, right? So we have this one to start with. The process starts at 400 Kelvin and 200 kilopascals. Okay, and then 200 kilopascals. Sorry. This is 200. Pressure axis units are very important when you're marking something on a diagram. Try to put the units always. And then the temperature, the initial temperature is 400 kelvins. This is 400 kelvins, right? And then it says the final temperature is given, right? So final temperature is 800, right? So assuming ideal gas behavior, find the specific work. Okay, so to find the specific work, we can use the polytropic process equations. Why are we using two graphs? Just to show how to draw a polytropic process in a TB diagram, right? So in an exam situation, you don't need to draw both graphs now. So let's go to the explanation here. So you can find the pressure used in this process, right? As the time is limited, so I'm going to do this. So this is the expression that we just derived, and then we can find P2 equals P1 into T2 over T1 to the power n divided by n minus 1, right? This is the power, right? So from that equation, we can get P2, which is 4031 kilopascals, right? Now we know that the pressure is 4000. Now we need to know V1 and V2 to locate our 2 points, right? Therefore, let's go again. So to find V1, we can use the ideal gas equation, right? Because pressure and temperature is given, and therefore we can identify V1, right? That is straightforward. And then we can use the polytropic relationship, or else we can use this equation to find the ideal gas equation to find the specific volume at state 2. So now we can see that V1 is greater than V2, right? So we go there. V1 is roughly 0.5 and V2 is roughly 0.05. So now we go up here. So this one. And V1 is, this is V1. And this is going to be V2. Then our process is going to be this, from 1 to 2. Right? So similarly, our process in TV diagram is going to be V1 here, V2 here, and so again the process is going to be a curve from 1 to 2, right? So if we want to derive a relationship between T and V, what we can do is to know whether this is a curve or not in TV diagram, right? So we don't know whether it's a straight line or a curve or whatsoever just by looking at it. So you can take this equation, and we can write this very same equation use as PV v to the power n minus 1 equals C. Just reconfigure the equation. Everybody agrees with this new form. It's just a reconfiguration. From ideal gas equation, we know that PV can be written as RT, right? If it is given in specific volume, right? So RT v to the power n minus 1 equals C. So again, T v to the power n minus 1. Sorry. C prime. So we see that this is a similar curve to this one. The power of the volume has changed a bit, so it's going to be a similar curve, right, from state 1 to 2. When you are marking the processes on a PV diagram or a TV diagram, it's very important that you mark the units, and that you mark the initial and final states, and you mark the path it follows, the substance follows during the process, and also the direction, very important, direction of the process, right? So direction of the process, initial and final states, and the values, every value that you know that is applicable. Anything that is confusing about this drawing this diagram? If n was 1, the relationship would be linear. No, it's not a good way of thinking that, because if n equals 1, what happens is PV equals constant. So then we can write P equals C into 1 over V, right? This is not a linear relationship. Did I answer your question, Kylie? Okay, so now the initial goal of this problem was not to draw this diagram, right? So what I wanted to do here is to give you an idea how to determine the properties so that you can draw these process diagrams, right? So the question asks the the process turn, the final temperature, assuming find the specific work. The question asks for that, right? If you want to find the specific work for a polytropic process, what you do is you go to formula sheet, and then in formula sheet you have few options. You check whether the polytropic index is equal to 1 or not. So if the polytropic index is not equal to 1, in this case, which is true, right? Polytropic index is not equal to 1, then you can use this equation. So there you have to substitute for pressure, volume, and polytropic index is given, right? So if you want to write this equation in specific work form, so if you divide the entire equation by mass, then the left hand side becomes specific work and right hand side becomes pressure into specific volume, P into specific volume at given state, right? And but by the ideal gas equation, we know that PV equals RT. Therefore, we can substitute these PV expressions using this equation, and we can arrive at this expression. RT2 minus RT1 over 1 minus N is the work of this given process, right? So you substitute and you come at your final values. So now find the initial and final pressure and specific volume for the process, right? So to calculate the initial specific volume of the process, we have the temperature and pressure given, and we have been asked to assume ideal gas behavior. And even if not asked for inert gases like hydrogen, it's fair to assume ideal gas behavior. Okay, so that is something you can keep in mind for gases like nitrogen, unless specifically mentioned that is not ideal. So it's safe to use ideal gas assumptions for gases like nitrogen or helium, something like that. Okay, so now we get this one from the ideal gas equation. That is clear? And it's clear? I assume it's clear. So if we look at this polytropic equation, okay, so P1 V1 to the power N can be written as P1. So what we have done here in this step is substituting for specific volume using temperature and pressure terms, right? So P1, sorry, V1 to the power N equals constant, right? So we can reconfigure this one as P1. This V1 can be written as RT divided by P. RT divided by P to the power N. From the ideal gas equation, we substitute the internal part here, right? And then when we solve this equation, we arrive at this expression that you see here. So now we have a comparison. Before moving forward, let's recap some of the characteristics of heat, work, and internal energy, right? So we just finished trying to interpret physical processes and draw the processes using the principles that we already know. And we tried solving the problems using ideal gas equations. But for closed systems, we can have non-ideal situations as well. So we'll discuss in the coming lecture how we can solve these problems. But to start the discussion with the first law of thermodynamics, let's recap what is heat and work and what is internal energy, right? So it is like when we look at heat and work, we can fairly say that it is an energy transfer mechanism, and both of these are not properties of a system. Work, can we say that it's a property? It's not a property. It depends on how we do things, right? It's not a state. And on the contrary, if you look at the internal energy, it's a property of a given system. So the interaction with the system, so work or heat has to cross the boundary between the system and its surroundings, right? So either heat enters the system or leaves the system, right? And then on the other hand, internal energy is a property that we have. Therefore, a system possesses a total energy and therefore an internal energy. So there's no boundary crossing involved. Internal energy is a property of the substance inside, right? So just to remind you the directions of these processes, when the heat comes in to a system, crossing the system boundary from the surroundings, then we call it positive, right? When the heat leaves the system, then we call it negative. On the other hand, when the work is done by the system or work leaves the system, then we call it positive, right? Then if we talk about the magnitude, for heat and work, the path does matter, right? So for states, the path does not matter. From state 1 to 2, if we follow path A, B, and C, the internal energy at state 2, does it change depending on the path we took? Anybody who can answer? It does not change, right? Internal energy is not a path function. So it does not depend on the path, but the conditions at that given state. Therefore, it does not change. But in contrary, if you look at the work done during process A, B, and C, right? So work done in process A can be highlighted as this, right? And if we followed path B, there's some additional work involved, right? There's some additional work involved as highlighted in this thing. So like the total work done in process B would be like this one. I just highlighted the additional work earlier. So this one. And if we follow path C, the total work would be this, right? Up to that curve, right? So now, are we all clear about that one? Being path functions and not path functions? Okay. Similarly, similar to work, heat is also a path function. So if we follow a different path, the heat transfer may differ. From A to B, the heat transfer may differ, right? So now we know these characteristics. Heat and work are path functions, and they are not properties of a system, but they have to cross the boundary to get their definition, right? And on the other hand, internal energy is a property of a system, and the system possesses total energy and internal energy. Therefore, that's a given value for the system. And also, it is a point function, or it does not depend on the path that we take during a given process. So we know the characteristics. Now, what we are interested in is quantifying. As engineers, we always need quantifiables, right? We need to size systems, we need to understand the energy balances, we need to do whatnot. Therefore, we are interested in numbers. So how do we relate these three parameters? So that is the discussion that we have to develop in the coming slides of this lecture, right? Before developing the quantifiable relationships, we have to understand the concept of system boundary and how it affects these quantities that we are talking about, right? So heat and work can depend, like the way we interpret heat and work can depend on the system boundary as well, right? So if we consider the first diagram, right? Here the system boundaries, the inside the box, the internal surface, and there's a heating element. There's a heating element which I colored by orange, which is connected to the surface, right? Not inside the boundary, but touching the boundary, right? And then that heating element is powered by an electric generator, as seen here, and that electric generator generates power by rotating this pulley that you see here. To rotate that pulley, we use this mass, right? So now, in the first case, the energy transfer between the system and the surrounding, anything inside the red box is the system, anything outside the red box is surrounding. So how does this energy transfer happen? Is it heat or work? Is it heat or work? It is heat. Very good. Because it happens due to a temperature difference, right? Anything that happens due to a temperature difference, any energy transfer that happens due to a temperature difference can be identified as a heat transfer. Therefore, that is heat transfer in the figure A, right? So now let's look into figure B. It has a different system boundary. In this system boundary, it's the outer surface. It's the outer surface of the box. Now, the heating element is inside. The energy carrier to the system is these two wires, right? So that, then in that case, this energy transfer, what can we say? Is it heat or work? It is work. Why? For definitely we can say it is not heat transfer, because the energy transfer does not happen due to a temperature difference, right? But like it is energy is crossing the boundary, so it has to be something. Now it is work. But some of you may be questioning, okay, the boundary is not moving, but still there's work coming into the system or done on the system, right? So if like the system boundary needs to move in order for us to have boundary work. So there's a specific term, boundary work. So in addition to boundary work, there can be work like this, right? Crossing the boundary by other means. Okay. And then the third figure. It encloses the entire system, and the piston and the weight is not going to change or travel across the boundary, right? So what can you say about heat and work transfer with the surrounding? Is it going to be zero? Yes, exactly. Because everything happening inside is within the boundary. So you remember from the previous slide, in order for us to define work or heat, it should cross the system boundary, right? If the system boundary can be imaginary or physical, it doesn't matter. So the way we define the system boundary is the idea that we are going to use to analyze our given problems. Depending on the context, people might have used the system boundaries we used in A, B, and C scenarios. It totally depends on the context. So if we select the system boundary as shown in C, then heat and work transfer is going to be 0. Can we, this is an imaginary system boundary, can we say this is an isolated system now with our imaginary boundary? Is it fair to say that? There's no physical barrier. There's the catch. It is not fair to say that, because there's heat and work transfer, like, which does not happen. Like, it's true, there's no heat transfer, there's no energy transfer crossing the boundary. But is there a real barrier for the mass to go in and out? Right? So that is the catch. So if the mass or energy can cross the boundary, then it's not isolated. Right? Is this a closed system? Is this a closed system? Scenario C, I am referring to scenario C, right? So is this a closed system? It is not, again, because in a closed system, what is the definition? The definition is the mass should not be able to cross the boundary. But does this boundary ensure that there's no mass transfer? Air or something can come, right? Unless this is located or placed in a vacuum, then it is a closed system and isolated. So there are two questions. I'll answer Alexandra first, as it's a shorter question. So which mass are we referring to? Like the air mass or any other mass can travel, right? Because this is an imaginary boundary. You know what I mean? Like the masses we see here is not the only substances that are around the system. In C, there could be gas coming in, right? Air surrounding the system. That's why I said, if we say that this is a vacuum, if this was a vacuum, then this is a closed system, and then again, as there's no heat and work transfer, then we can even call this an isolated system. But this is not located in a vacuum, so if this is in just surroundings, so any air or anything can come in and go out, right? So yeah. So back to Alan's question, just to confirm, so heat is positive when done on a system, negative if it leaves the system. That's right. And work is negative when done on a system, positive if the system does it. That's right. Both of your expressions are right. So yeah. Okay, so now do you understand how important our system boundary is for our analysis work, right? The numbers that we pick for work, heat, and everything, it totally depends on the system boundary. So in this figure, you have a description. So a gas is compressed in a well-insulated piston cylinder device. As a result, the temperature of the gas increases. If the system boundary is set up as shown, is the energy transfer due to heat transfer or work transfer? So for now, let's assume that this surface is a moving boundary which touches the piston. It touches the piston surface, right? So when the piston moves, the system boundary moves. The red portion of the system boundary moves, right? Red portion is this one. Okay, now the system boundary moves. So is it work or heat transfer? Why it is work? Because there's no heat transfer. There's no energy transfer due to a temperature difference, right? It's only happening due to a moving boundary. So this is boundary work, right? That is very true what all of you said. And then if this boundary is set up as shown, is the energy transfer due to heat transfer or work? We answered that. Is it positive or negative? When the piston moves from state 1 to 2, it is negative, right? So it's simple to remember. If you think when a system is contracting, the work done on the system, therefore like we can say it's negative work. When the system contracting, then it's negative work. When it's expanding, it's positive work. Simple to remember. So if the process was from 2 to 1, then we can say that it is positive work. So some of you may be thinking, how can be work positive or negative, right? Work is not a vector or something. But like this is just a sign convention. These positive or negative numbers, quantities, like putting positive or negative, is a sign convention that we use for us to be on same page when we are analyzing systems for everybody. So every engineer knows, okay, this is what they mean by positive work, right? So it's not that positive work means it's a, I mean, it has a direction and it's a vector. No, work is not a vector. But this positive negative indicates a sign convention or gives us a reference to discuss, right? Now, the most important slide of the day, the first law of thermodynamics for closed systems. Right? Before moving forward, what is a closed system? A closed system, in a closed system, the mass cannot cross the boundary. So therefore, which essentially means there will be no mass coming into the system or no mass leaving the system. Such a system can be called a closed system. Still, the important fact is the energy can cross the boundary, right, in the form of heat or work, right? Now, if we have this system, this tank that we see in the bottom right hand corner, and if we want to find the energy difference occurred from state 1 to 2, like at this time at 10:10 a.m. we had E1 energy, and we are interested in finding the energy at 10:15 after a certain process, right? So in order for us to do that, what we are interested in seeing is the state 2 energy level minus state 1 energy level, right? But we cannot directly calculate the energy level of a given state, right? So it needs a lot of efforts. So what we can do is we can check how much heat the system gained, right? How much heat the system gained, that is Q12, during the process, how much heat we gained. And you remember this heat, if gained by the system, we call it positive, right? If leaving the system, we call it negative. And then we need to reduce the amount of energy that we transferred by doing work, right? Doing work. So again, if the work is done by the system, it is positive work. If it is work, if work is done on the system, it is negative work. Okay. Okay. Now let's try to understand this. If, let's say, in a given process, we lose heat of 10 kilojoules, right? And again, the work done on the system is 5 kilojoules work, right? So now, can you say the total energy change of the system during this process using the equation we just learned? Can anybody give me the answer? Can anybody give me the answer? Okay, let's try to see this. Okay, now what is the amount of heat that we substitute in this equation? The magnitude is 10 kilojoules, and it is in the system. Therefore, is Okay, and there's a negative sign in the equation. Now we have for our work, and it's done on the system. So therefore, should we negative 5 or 45? It is the negative 5, right? Done on the system. Now, what is the answer? Minus 5 kilojoules. Are we clear how we arrived at the solution? Right? Straightforward, but this gives a very important idea, right? So if we do use different signs, like where we should use a negative value, if you use the positive value, what you get is a very wrong answer, right? So please be very careful in that aspect. The sign convention of heat and work when you are using it in your first law equations. Okay, now the other relationship that we learned in lecture 4, right? This one, you remember, we knew that the total energy change of a system during a process is equal to internal energy change, which is U2 minus U1, and kinetic energy change plus the potential energy change. And if the system is not moving, if it is stationary, the box or tank is somewhere, if the piston cylinder mechanism totally is not moving here and there, right? The piston is moving up and down, but the entire system is not moving from one place to another. So in that case, what can you say about the kinetic energy difference and potential energy difference of the substance inside? Excellent. So we can say these are 0, right? Then it leaves us with this expression. So it can be said that the total energy change of the system, of a closed system during a given process, can be given by the internal energy change, right? So now from equation 1 and equation 2, we can say that the internal change of a closed system during a given process can be expressed as shown here. Internal energy change of a closed system during a given process can be shown as given here. So do we all agree with this one? Do we all agree? Perfect. So now this equation is a very important equation that you will be using this quite often. Okay. So the very same equation. So energy change of the system and is equal to heat transfer minus the work done by the system. Heat gain minus the work done by the system, right? So if we differentiate the entire equation by time, we can get a rate form, right? So energy change of the system per given time, per unit time, is equal to heat transfer during that given time interval minus work done by the system during that given time interval, right? So it is very important in these two instances, the units change. If it is just the energy balance equation, as we learned in the previous slide, the unit of energy is joules, right? When it converts to rate form, what we are dealing with is joules per second. In other words, watt. So these are the SI units for those terms. And you may be wondering, do we need both these equations? Right? Yes, we do need. Why? Because, for an example, let's say you are going on a camping trip and you want to boil an egg, right? So you have a few propane cans and then you try to use those cans to boil that egg. You need to know what is the total energy required to boil that egg in order for you to know that you do have propane cans. If you don't have enough propane cans, you might not be able to generate enough energy to boil your egg, right? So that is where we need the energy balance equation. So why do we need the energy rate equation? Okay, because we need to make sure that our stove can generate enough energy in a given time interval to boil our egg within a given time. We don't want to wait the entire day. In the morning, we put the egg and we wait until evening and still not boiled, and we wait for the next day. We will die out of hunger, right? So we need to know, we need to ensure, okay, I can get this egg boiled within 5 minutes or 10 minutes, right? Are we all clear why we need these two forms, the rate and the cumulative energy, like the energy balance form? Are we getting a sense? Perfect. Now, let's see how we can use these relationships to interpret some of the known processes, right? So, this is a familiar figure for you. In the first lecture, I introduced you this. This is your very own refrigerator, right? So you have your pop bottles, vegetables here, and your refrigerant absorbs energy from these so that they remain cool, right? And after that, your compressor compresses the refrigerant and increase the pressure and temperature and send it to the condenser, and condenser ejects heat to the outer surrounding, and then they send it back to an expansion valve so that it arrives at the same condition as it was before to enter the evaporator. Okay, now my question to you is there anything special? I don't want you to know the principles of refrigeration cycle yet. What I want you to know is there anything that you see in this process? You don't know refrigeration cycle, but is there anything special about a cycle? What would we call a cycle? Okay, so before answering that, I have another question. What would be an appropriate system boundary to analyze this problem? We need to analyze the energy flows coming in and going out of the refrigeration cycle, right? So you see that there's a QL, heat being absorbed, heat being rejected, and work being inputted into the system. So now, in this case, what would be an appropriate system boundary to analyze what's happening to the refrigerant inside this one? The steps, okay. So would it be appropriate for us to draw a system boundary like this? We can do that because like there's work coming into the system, crossing the boundary, and heat that we emit crosses the boundary, and there's a heat absorbing that adds heat into the system, right? Okay, so to be more accurate, we could have just picked all the surfaces wetted by the refrigerant inside the cycle. So then nothing else, the refrigerants only. But for our calculations, it's fair to assume a system boundary like this. I mean, we know what we are referring by this system, right? So now here we have an heat input, work input, and heat outlet, right? So now we know that there's three things that is crossing the boundary. Okay. Now back to my original question. What is special about a cyclic process? What is special? So if we draw a PV diagram, the cyclic process arrives at the same initial state after going through a sequence of different processes. Do you agree? The initial and final states of the process should be same. That is why we call it a cyclic process. And then this brings us to an important notion. Can anybody guess? What can you say about the total internal energy difference after this cycle? No change. Very important. Very good. Delta U equals 0. Right? Now, we have established that this is not the refrigeration cycle, PV diagram of the refrigeration cycle. I just draw it because we will be learning the refrigeration cycle in detail in the coming lecture. So I'm not going to discuss that in detail, but we will discuss what is relevant to today's lecture, right? Now, delta U equals 0. Now, the question asks us, considering the thermodynamic cycle, find the relationship between W in QH and QL by using the first law, right? So you remember I said that delta U equals Q. In this case, it is not 1, 2, it is Q cycle. I will put QC, Q cycle, minus W cycle, right? Now, what do we want to find? The relationship between the heat inputs and the work input, right? So now there, you know that from process during this cycle, the heat transfer is 0. We established that. So we can say that 0 equals Q cycle. I will put QC. No, putting QC would be confusing. Okay. Now we can substitute for value. What are the heat components that is involved? QH and QL, right? So QL is coming into the system. So what is the sign of that one? QL is coming into the system. Is it positive or negative? It is positive, right? So we can start substituting. Du is equal to 0, and we have a positive heat input, QL. And what are any other heat components? Yes, we have QH. It is leaving the system. Therefore, we know that it's negative, right? Minus QH. And now we have to subtract the work done by the system, and we have a work component coming into the system. Is it positive or negative? Work coming into the system. Work coming into the system is always negative, right? Therefore, we put negative. W in. So like when you are substituting the values to QL, QH, and W in, you just substitute the numbers. Now we have already applied the sign, therefore, that's why, right? So therefore, you can say that W in equals QH minus QL. right? This is the relationship that we were looking for. So now you see how we can apply the first law equations to identify the energy balances of some important processes, right? Any questions so far? I assume none. And we established this form earlier of the first law of thermodynamics, and the rate form is given here. And in an adiabatic process, there's no heat transfer, right? So in an adiabatic process, the heat should not cross the boundary. That's the meaning of an adiabatic process. Therefore, we can write in the first law of thermodynamics, the rate form and the energy balance form, both without the heat component in an adiabatic process. Are we clear on that one? Perfect. Okay, now to summarize the solution process for first law questions or any thermodynamic question that we are going to do in this course. The first one, sketch a physical system, right? So you can sketch the system and pick up proper system boundary, because drawing the physical system is important, because that gives you a sense what's happening when it says a piston cylinder mechanism. Try to draw it, and then so you say, okay, now this piston goes up, and are there any stops or not, and then you have a sense, right? And then after picking the system boundary, indicate heat and work transfer in and out of the control mass or the system boundary, right? Note down the signs, very important, like whether it's going out or coming in. So you mark the numbers there, right? And then identify the important processes, right? So is it isobaric, isothermal, polytropic, isochoric, right? So it could be anything. So you have to identify these important processes that define that given process so that you can calculate the properties, right? Then you have to indicate that in a PV diagram or TV diagram. I would personally start with a PV diagram for any question up to this point. I will start, unless specifically asked to use a TV diagram, I will use a PV diagram. Why? Because the area given covered by the curve, by a given curve, in the PV diagram have a meaning for what we have learned so far. It is the work done during a process. The area covered by a TV diagram also has a meaning, but it is not relevant to the context that we have discussed so far. The area of TV diagrams will come into play once we discuss the entropy. There, it gives the heat transfer during the process. So, but for now, I will start with the PV diagram, okay? And then I will write down the first law equation, and then eliminate the terms that are not applicable, like make it zero. If it is adiabatic, make the Q terms zero. If it is a cycle, make the internal energy difference zero, right? If it is a rigid container, then there's no boundary work, right? So make the W term zero, like that. And then after defining these things, we need the states to calculate the amounts of energy that is being transferred during this process, right? So in order to do that, we can use ideal gas law or thermodynamic tables or other physical laws like mass conservation, and also the spring forces applied, all the physical laws. In addition to, like, we can use ideal gas law if it is an ideal gas, or you can use thermodynamic tables if it is a real gas, right? So this is the solution process for this kind of problem. And I know that I have hit 10:30, so I will stop the lecture here. And the last question, there's a question after this slide. So we'll discuss it in the next lecture on Friday. And I have a good news for you. By this point, you have covered the necessary theory for your midterm as well. So now you are good to complete your midterm, right? But we have to do some more practice questions so that you understand it better. On lecture 7, we'll focus more on practice questions. And what I'm trying to say is you are good with the theory for the midterm. Okay. So this is the question. We'll discuss this in the coming lecture. So thank you very much, everyone, for your time and patience with me. And if you have any questions, you can stay